So we're going to start off talking about chemical bonds, and there are three basic kind of bonds that we need to know about. First is ionic, electrostatic attraction between ions, meaning the plus charge of the cation attracting the negative charge of the anion, forming a crystalline structure, a big lattice structure. Then there's covalent, sharing of electrons, forming molecules. And then finally we have metallic, which we have not talked about, and we won't talk a whole lot about it, but these are metal atoms bonded to several other atoms. And it's neither ionic nor covalent for the bonding model. So we're going to start off talking about ionic bonding and the energetics of ionic bonding. What are the energy changes? Well, we can say that it takes 400, if we talk about sodium chloride, let's talk about sodium chloride, because that's always the favorite ionic compound to talk about, because everybody's kind of familiar with it. If we talk about the energy required to remove the electron for the sodium, it requires 495 kilojoules per mole. This, of course, is known as the ionization energy. We know that we get back some energy when that electron goes to the chloride atom. And the amount for sodium chloride, or anytime chlorine accepts an electron, it releases 349 kilojoules per mole. Okay. Let's watch a quick little video on the formation of sodium chloride. Hopefully this will... I was having difficulty finding the play button.
Sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
I like how they say the exothermic reaction. A little bit. Do you see all that energy released? Okay, so the energetics of ionic bonding. Those numbers, the ionization energy of sodium and the electron affinity of the chlorine atom, don't explain the reaction of sodium metal and chlorine gas, why that reaction is so exothermic. So there's got to be something else to this puzzle, okay? And that is the electrostatic attraction between the newly formed sodium cation and that chloride ion. And that's really what we call the lattice energy. And it's the energy that's required to completely separate a mole of solid ionic compound into its gaseous ions. And that's almost always how they experimentally determine like a bond energy, is they always break things apart. How much energy does it take to break that bond? Right? Now, the energy associated with this electrostatic interaction is governed by Coulomb's law. Kind of refers to it a little differently, in that it lists the delta H standard conditions for the lattice equal to capital K, lowercase n m, over R of m to the n plus R of x to the m minus. This assumes that you have an ionic compound that uses the, ready? I'll try to draw this. Oh, that's supposed to be a circle. In here is your M ion to the cation to the N plus charge. And this is your X anion to the M minus 1 charge. Okay, so K is a constant that depends on the geometry It's a constant. We don't have to really do much with this equation. Okay, so that's the constant based on the geometry. The N and the M are the charges for the ions. This is the radius of the cation plus the radius of the anion, right? So it's very similar to what this equation is. Actually, it's the same thing. It's just written a little differently. And I wanted to make sure that you saw this equation because this is the IB equation. So when we talk about problems and things, this is really the equation that we should be using. So lattice energy. Lattice energy, if you notice, the charge of the ions was in the numerator. So as the charge increases, so does the lattice energy. If you look at I'll find one. Well, if we look at lithium compared to magnesium chloride, oops, I guess I should be looking at this one. That's 800 kilojoules. Magnesium with the +2 is 2,000 kilojoules. So hopefully you can see that as the charge increases, the lattice energy increases. It decreases with the size of the ions. So if we look at, oops, sorry. Having trouble. If we look at sodium fluoride compared to lithium fluoride, lithium is smaller radius than sodium, so that's going to be the only difference, and you can see that the lattice energy with the smaller ion is less than the larger one. Okay, so lattice energy increases with the charge, it increases with the decreasing size of the ions. Okay, we'll look at that as an opener. Okay, now this was gone over in class. This is known as a Born-Haber diagram, and it's the energy. Okay, so we're going to talk about energetics of bonding. We can account for the three energies, and using Hess's law, get an idea of the energetics evolved in the process. This is known as a Born-Haber diagram. Don't believe that you're going to be asked to generate one on your own, but you should be able to analyze it. And overall, what we're going to look for is seeing if we can account for or calculate the lattice energy for sodium solid, sodium chloride solid, going to its gaseous ions, which is the definition of lattice energy. Okay, the decomposition of a solid ionic compound into its gaseous ions. And if we look, we can, using Hess's law, go about it from this angle. If we add up all these enthalpy changes and subtract this enthalpy change, we can get the overall lattice energy for sodium chloride. Well, what are these different enthalpies that we can look at? Well, if I take the elements of a compound and their standard states and put them together to make a compound, that is known as the enthalpy of formation. So if I take the negative of the enthalpy of formation for sodium chloride, I can go from the solid ionic compound to the elements in their standard state. Eventually, remember, I want to get to these ions in their gaseous state for both those elements. So one of the first things you can do, and it doesn't matter the order in which these are done, I need to take this sodium solid and go to sodium gas. Well, that's the heat of formation for sodium gas. That's this energy change. Next, I need to, instead of having half of a chlorine molecule, I need to have the gaseous chlorine atom. That's the heat of formation of chlorine atom gas. Awesome. So now I need to change something into an ion. Well, let's take the first ionization energy of sodium, and that will give me sodium ion plus that electron. The enthalpy change when this electron goes to the chlorine atom to make the chlorine ion is known as the electron affinity for chlorine. So if I add up all these enthalpy changes, subtract the electron affinity for chlorine, I will get the lattice energy of sodium chloride. that's how lattice energies are typically found, because you can't experimentally determine them with any ease. Okay. These phenomena also help explain the octet rule. Why do things want to get 8 electrons? Okay. Metals stop losing electrons because once they obtain that noble gas configuration, that lattice energy is not enough of a change to make the overall reaction occur. It doesn't make it more stable. There's not, if you notice, reactions are the difference between the energy required to break bonds and the energy required to make bonds. A lot of spontaneous reactions are exothermic because the energy released when you make those bonds more than makes up for the energy it takes to break the bonds. So that's what you look for. Here, the metal isn't going to lose any more once it gets to that octet because the making of bonds after that is not going to be enough of an energy change to make up for the energy required to take those electrons away. And that's where this screencast will stop.